So thank you everyone for coming to this session. My name is Mike Furr. I'm an engineer with AWS in the EC2 organization. And today I'm going to be talking to you about network performance. So this is a 400 level talk, so we're going to go pretty deep. We're going to be talking about TCP performance. I will give you a little bit of a gentle ramp up to kind of get your minds engaged and kind of in that networking mode. And after we kind of start talking about TCP, we're going to talk about what makes it go. You know, what are some of the things that are going on kind of under the covers when TCP is running underneath your application. Then we're going to look at some tools to try to inspect what decisions TCP is making. These tools can kind of pull back the wool on the black box, which can be the network. And they can give us really good insights. And then I'll show some examples of how we can change some of the parameters of TCP to alter our performance. A lot of the examples in this talk are going to be in Linux, but of course TCP is a cross-platform technology. All of his examples port equally well to Windows, but just to keep the talk concise today, all the examples I'm going to show on the slides are actually Linux-based. And then the last part of my talk, I'm going to have some sample applications where I'm going to demonstrate what happens when we start tuning TCP under various different conditions. These sample applications are not necessarily meant to be exact replications of real-world scenarios. They're really more here to demonstrate what effects these tuning techniques have. And what I hope you take away from this talk is actually a new set of tools in your toolkit rather than an exact performance analysis of these particular applications. So as a little bit of a spoiler, and to keep you in your seats because I know it's Friday, one of the applications I'm going to be showing at the end is actually going to increase its performance by 137%. And this is a change I'm going to be making without touching the application itself. So I'm not going to be touching the code. I'm not going to be changing the application in any way. I'm just going to be manipulating the Linux system I'm going to be running it on and just playing with some of the TCP tuning parameters there. So I've been working at Amazon for a little over 7 years now, and I really love working on the cloud. And I've spent almost all my time in that duration in the EC2 networking organization. And so I've really come to love TCP2. So TCP, of course, is the transmission control protocol. It's the protocol that underlines most, not all, but most kind of application layer protocols out there. So, if you're remotely administrating an EC2 instance over SSH, that's, of course, going over TCP. Same with browsing the web or sending an email from your phone, all running on top of TCP, right? And TCP, while it's the dominant one, of course you have other options such as UDP and others. But the reason TCP I think is so popular is for a couple of reasons. One is that it gives you kind of a streaming delivery kind of abstraction for your application. So when you instantiate a TCP connection, your application gets a socket where it can read and write bytes to, right? The application doesn't have to concern itself with what happens to those bytes after it writes to the socket. It's TCP's job to make sure all the bytes are delivered to the other side, that none of them are dropped, none of them are duplicated, and they aren't reordered in any way. The second thing that TCP does for us is it dynamically adjusts to the current networking conditions, right? So if the network has a shift in behavior, TCP will adjust its behavior and is always trying to maximize its throughput based on what it perceives to be the current network condition. So let's start talking a little bit about what TCP looks like kind of from a high level, right? So when you ask most people about TCP, the first thing they say is, well, there's a three-way handshake, right? And the three-way handshake is there to establish a connection, right? So TCP is a connection-oriented protocol. And the abstraction we oftentimes think about is after you establish this connection, you have a two-way bidirectional pipe between two endpoints. So here, let's say I have two Linux instances, Jack and Jill. And after establishing the three-way handshake, they now have a bidirectional communication pipe to send. This pipe is fully duplex. Jack and Jill can both send and receive simultaneously. And it's kind of a nice abstraction for application programmers to view. However, when we start looking at actual TCP performance itself, it often helps to kind of go a level deeper and not think of this as one connection, but rather a pair of unidirectional connections. The reason this is important is the path that packets take from Jack to get to Jill might be a very different path than Jill takes to get back to Jack. They might take paths in that they traverse different routers, or that they might go through the same routers, but the particular interface buffers they hit might have very different properties. For example, if you're sending a stream and there's a lot of people who are concurrently streaming a live video stream, there might be a lot of contention in one side of this transfer, but not in the other. The other big reason it's important to kind of view TCP connections kind of as two separate unidirectional sides is the main control mechanism we have is actually at the sender. When a receiver receives a packet, it has a very limited state machine to figure out what to do next. But on the sender side, it actually has quite a bit of opportunity to figure out when and how often it should put packets on the wire. So when you're thinking about TCP and performance, the number of bytes that are actually in flight at any given time turns out to be one of the most important things to tune when trying to optimize the flow of a TCP connection. There's two main factors that go into into performance of TCP, and these are the receive window and the congestion window. Hopefully this isn't a blast too much for the past, but just to give you a little bit of a ramp up on these. So the receive window represents a buffer on the receiver side. It's managed by the receiver, and it's signaled to the sender. And the point of this buffer is that it's maintained kind of in the kernel in the TCP stack. So as bytes are coming off the wire, they're put into this buffer in the kernel, and then it's up to the application from time to time to reach down into the kernel and do a read system call and read those bytes up into the application. So of course what this means is that if the application is not reading those bytes out of the buffer can fill up, and if the buffer's full, there's no point in Jack sending any more data to Jill if Jill's buffer's full, right? So that's one of the reasons why it kind of signals this buffer size back and forth. The other important thing to keep in mind with this receive window is we need to keep in mind the round trip time between these two instances. And the reason that's important is that when we're talking about bytes on the wire and round trip times, the usual equation we have is what's known as the bandwidth delay product, right? The bandwidth delay product says if I have a particular bandwidth and a particular round trip time, if I multiply those two together, I get a total number of bytes I can have in flight at any given time. Now what I've done here on this slide is I've taken that equation and I've kind of solved for a different field, which is that if I know my receive window, if I know the number of bytes I'm going to have in flight at a given time, let's say 100 kilobytes, and I know my round trip time, I can't really change the speed of light very often, let's say I have a round trip time of 2 milliseconds, then the maximum effective bandwidth I can get on this TCP connection is only 400 megabits. 400 megabits is actually pretty good, right? A lot of applications will do very well with 400 megabits, right? But of course, not all applications have the luxury of a 2 millisecond round trip time. If I took this same number of bytes on the wire and I changed it to a system that were separated by 100 milliseconds, then the throughput that I could effectively get on this connection would drop all the way down to 8 megabits. So nothing else has changed in the system other than the round trip time. And of course, 100 milliseconds is not that unreasonable. It's about the time a packet would take from the East Coast to the West Coast and back again across the United States. So again, this is not related to how big of a piece of fiber I have, how many waves are on it. There could be a lot of available bandwidth, but my effective bandwidth is limited by how many bytes are in flight. So it's really important that we stay on top of what's going into these decisions that TCP is making to make sure it's maximizing and is able to fully utilize the bandwidth that might be there and not artificially limit itself. So here's a couple examples from Linux. These are actually, I run all these on Amazon Linux if you're trying to run them at home, but these are pretty standard across almost all Linux distributions these days. So this first sysctl is setting the maximum receive window for kind of all IP protocols across the box. The second sysctl there is doing it specifically for TCP, and TCP actually takes a 3-tuple of values. It takes a minimum, a default, and a maximum. And so if you have a maximum TCP receive window that's too small, no matter how hard TCP tries, it might never be able to take full advantage of available bandwidth. Okay, let's talk about the congestion window. The congestion window is a little bit trickier. The role of the congestion window in TCP is that it's trying to figure out if there's congestion somewhere in the middle of the network. It's maintained by the sender, and it's trying to figure out how fast should I send data across the wire? Because if there's congestion and I send too much data, it's very likely some of that data will be dropped. So it's trying to play a game to figure out how fast can I send and kind of optimize my chances that all the data will eventually arrive at the other endpoint. The inputs to try to figure out what to set the congestion window to kind of vary based on what implementation of the congestion control algorithm that is in use. There's a few different inputs out there that these different algorithms use, but most of them use two different inputs as their kind of primary signals. One is loss. So in other words, if I'm sending a stream of packets across the wire, if one of the packets doesn't arrive, then I know something might be going wrong in the middle of the network. The second one that these algorithms use is latency. So how long does it take for my packet to maybe go from one side of the connection to the other and perhaps back again? These aren't the only inputs that algorithms use. There's some other ones out there. Some of the algorithms will use explicit signaling, which kind of more directly signal back and forth what both sides think about congestion. And there's some algorithms out there, and I'm going to mention this a little bit later, that will actually try to figure out the spacing between the packets to try to guess just how congested the network is. So when trying to set the congestion window, the TCP congestion control algorithms have a difficult job. When they start out, they have no idea what the state of the network is. They have no idea if there's loss. They have no idea what the latency is. All they know is they have this destination address that they would like to send some packets to. So the way it starts out is it uses what's called an initial congestion window. And the initial congestion window is the number of packets that it puts on the wire before waiting for its first acknowledgement. So with an initial congestion window of 3, it'll put 3 packets on the wire. And let's assume we have a 1500 byte MTU. That means each packet is going to be about 1448 bytes. And our total number of bytes on the wire before waiting for our first response is only about 4300 bytes. So I send out 4300 bytes, I wait for a response, and then after I get a successful response, hopefully, the TCP algorithms will typically ramp up very, very quickly to try to figure out just how big of a congestion window I can use before I start to see impact from the network. Now 3 is a default, but there's no reason we can't change it. And the way we change it is actually on a per route basis. So if we would like to change the route, if we would like to change the initial congestion window for one of our routes, we can do it with this command here. So this IP route change command will, when appended with the initial congestion window value, will update it. And again, this number is in packets. And so you can find, when you do the math, it's really the number of maximum segment sizes that it will allow to go into the network. And then if I print out my routes again, by default, it won't print it if it hasn't been altered. But once I do change it, you can see that it now shows up in the updated output of listing my routes. And now I've updated that initial congestion window to 16 packets. And at 16 packets, I've now gone from, instead of 4,300 bytes from waiting for my first packet, to almost 23, or over 23K before I wait for that first acknowledgement. So this is going to be a really important difference, especially if you have very short-lived connections that transfer a small amount of data, right? Think about web pages, HTML files, thumbnails. A lot of connections have this property that only lasts for a very short amount of time and only transfer a relatively small amount of data. And so this can actually really have a meaningful impact to this, and we're going to look at this in one of the example applications at the end of the talk. So let's talk some more about loss. So this is a graph that shows what happens when you start to have loss on a TCP connection. The y-axis here is kind of your percent of idealized throughput. So at 0% loss, you're getting 100% of your idealized throughput. As you start to see more and more loss of the network, the throughput of the connection will drop off dramatically. I think it's almost counterintuitive. If you'd ask someone, hey, I have this TCP connection, and 1% of my packets are dropped, which means 99% of my packets are actually getting there. What percent of my throughput would I expect? Maybe not 99, maybe I'd say 95 or 90, but that's not the case at all, right? It actually drops off very, very quickly. And part of that is the actual TCP algorithm itself. When it detects loss, it self-throttles itself. It really pulls back and tries not to kind of pile on and make the situation worse. So loss has a very, very important role in just how fast our applications can run. The other takeaway from this graph is somewhat of the inverse, which is to say, if you have an application and suddenly that application starts performing very, very poorly, one potential candidate that could cause that would be loss on the network. So let's look at some tools that we can use to try to figure out, am I seeing loss, and is that contributing why my application is actually slowing down? So the first tool I'm going to talk about here is the netstat tool. This is probably the most well-known tool that I'm going to talk about today. Netstat is pretty standard. You'll find it on just about every Linux distribution out there installed by default. And it gives you lots and lots and lots of data about a lot of different things related to sockets. So I'm showing some output where I'm just grepping out the number of retransmissions. So in TCP, a retransmission is when I send some packets and I fail to get a response within a particular window. And so what that means is that either the packets I sent to the receiver got dropped, or the response they sent back to me got dropped. In either case, I don't know what happened, and so I have no choice but to resend the packets that did not arrive. And so this is what we call a retransmission. So if you ever see a retransmission, what that means is that your TCP stack thinks that the packets it sent the first time did not arrive. Now, netstat, while it's very useful, is also very coarse-grained. It actually, these counters are for all of your sockets across the entire box. And so you won't be able to differentiate which connection is actually seeing these retransmissions. These counters are also initialized when Linux boots. So even though you might see 58,000 retransmissions, you don't know if that happened 10 seconds ago or 10 weeks ago. And so to be useful, you're going to have to pull this tool and look for shifts in the number to try to correlate when you might be seeing loss based on when the number of retransmissions changes. So we can do a little bit better than netstat. Another tool that's a little bit less known but is also commonly installed is called the socket statistic tool, or just SS. So this tool has a bunch of options. I showed a few here, and it gives you a wealth of information. And the socket statistic tool, what it does is it actually gives you per socket information. I'm not going to go through all these, but I'm going to touch on a few of them. So the first one we can see here is the state of the connection. So if you're interested in looking just at established connections or one in a particular TCP state, you can certainly grep those out. Excuse me. The second number here is the send queue, right? So the send queue is a buffer on the sender side from when the application does a write system call down to the TCP stack until those bytes are actually transmitted onto the wire. So if you see this number just continually at 0, what that tells you is that your application just isn't writing any data. So it's very healthy to see this number kind of constantly being at a good value, because that means the thing that's blocking your system is not your application, but it's actually something in the network. So you kind of expect to see this number on an active TCP connection to be continually, greater than 0. Next, we have this word cubic. It's a little bit of an odd word right in the middle of this text, of this wall of text. Cubic is actually the TCP congestion control algorithm that this particular connection is using. We're going to talk a little bit more about that in just a second. And then we have the retransmission timeout. So when you don't get an acknowledgement, at some point you have to make a decision about how long to wait, because the acknowledgement might be on its way, right? The acknowledgement may not have been dropped. It might just be experiencing some latency on the links, and it might not have shown up yet. So this number is the number of milliseconds that this TCP connection will wait until it initiates a retransmission for a packet that has not yet been acknowledged. Next, we have the congestion window. So this TCP connection is ramped up to 138 packets. Again, this number is in packets, not bytes. And then finally, the number of retransmissions for this particular TCP connection. So this TCP connection is actually seeing about 11,000 retransmissions. So it is probably experiencing some loss somewhere on the network. We can actually do a little bit better than SS. There's some really great open source tools out there. This one is by Brendan Gregg. So Brendan is an engineer at Netflix, and he has a really amazing performance blog. I highly recommend you check it out. And what Brendan's tool does here is it actually uses the kernel instrumentation framework to actually instrument the TCP retransmit SKB function in the kernel to gather some information when a retransmission happens. So this is advantageous for a couple of reasons. One is that because we're actually instrumenting the particular kernel function call, it only gets called when there's an actual retransmission, which basically means you get a trigger, right? You can run this command and you'll see, as retransmissions happen, they'll start showing up on your screen. The other nice thing about this is that because you're in the kernel, you have easy access to more information. You can actually get a lot more information than just this. This is kind of the default. But right away, we can see that we've already got the process ID, which is really helpful to track back this particular TCP connection was initiated by this particular process running on my box. And so it can be very helpful if that's the process ID of my web server or maybe my mail client or whatever. And so having additional information at our disposal really helps us kind of try to triangulate what's going on. So definitely take a look at this tool and play around with it. It has a lot of really cool options. The other nice thing about it is because it's instrumenting the kind of the exception path, so it's instrumenting the retransmit function, that means it's only called when the retransmits happens, which means the overhead of the instrumentation is only paid when you have a retransmission. So it wouldn't affect the performance of your TCP connection on kind of the normal happy path. Only when you actually see a retransmission does it actually execute this instrumented code, which is a little bit nice. Okay, let's dig some more into the congestion control algorithm. So the congestion control algorithm really is the magic in TCP. And it's magical because it has to make almost an impossible decision. The TCP congestion control algorithm is looking at just local information. It's trying to figure out, it's looking at the different packets that are arriving, and it's trying to make an inference about what's going on kind of in the global network at a particular point in time. And of course, the state of the global network is going to be changing over time. And so the congestion control algorithm has a very difficult job in that it has to kind of take clues and use heuristics to come up with a decision about what to do next. So if you look at the history of the congestion control algorithm on Linux, you can see it's actually changed several times over the years. So back before 2.6.8, it was actually an implementation called New Reno. Starting at 2.6.8, it actually switched to something called BIC. And now the modern builds of the kernel actually use something called Cubic, which we saw before with the SS tool. There's a bunch of other implementations out there. It's actually a fascinating area of research if you want to learn more about TCP and what goes into building these algorithms. I definitely recommend digging in and reading some papers about what are the design decisions behind each of these algorithms. But one of the nice things that Linux gives us is it has a pluggable architecture such that we can swap out which algorithm we want to use. And that's really important because just because there's a default algorithm, it doesn't necessarily mean that that default is going to apply to our particular use case. And the other thing you can take away from this, when I see a fundamental aspect of my operating system change several times over a time period, you can kind of take a step back and think, well, why can't we get this right? And I think the first reason, which is what I already touched on, is that it's a hard problem, and so we're going to continually iterate on trying to solve this problem with better heuristics. The other thing that's happened is, the network itself looks very, very different over the years. It's really transformed several times. If you think back to 10, 20 years ago, there was broadband. Before that, there was dial-up. Then we had Wi-Fi, and now there's a huge mobile set of devices out there that are running TCP applications. And so when you think about all these different kinds of network topologies, it's really a very different perspective for these algorithms to have to handle if I'm on a mobile network versus a broadband network. And since your particular application might be targeting customers in one of those segments and maybe not both, it might behoove you to try to investigate, are there different TCP congestion control algorithms that can take advantage of my specific situation? So if we want to tune exactly which algorithm we're going to use, the first thing we can do is see what are our options. So here's a sysctl, and this is just asking the kernel, what TCP control algorithms are available to me on this box? So on this particular instance, I have Cubic and Reno. But there's actually a large number of these algorithms that actually come pre-compiled in a lot of the standard kind of kernel images for Linux distributions. And we can just find those in the kernel tree just by using that find command there. So anything kind of prefixed with TCP underscore is probably going to be a congestion control algorithm. And so if we want to try out a new one, let's try out one called Illinois. That sounds fun. So we're going to mod probe Illinois. So that just loads that kernel module into the kernel. And then lastly, we're going to update our, use that sysctl to update the list of available congestion control algorithms to include Illinois. Now at this point, Illinois is simply a choice. It's not what network processes are going to use going forward without a little bit of help. And when you look at what a lot of applications out there do, very few of them actually expose this configuration knob. It's a very low-level detail to pick what congestion control algorithm you want to use when you set up a TCP connection, right? It's not in your general, result when you first learning how to open a TCP connection, when you're first learning how to program. And in fact, even the most advanced servers out there typically don't expose this all the way through like to configuration files. So one way for us to play around with this, however, is just to update the system-wide default. And therefore, any new connections going forward after we update the system-wide default will then start using our new algorithm. So that's what these commands do here. The sysctl at the top is updating the in-memory kernel to set the Illinois congestion control algorithm to be our default. Of course, the downside of using that command is that it only lasts as long as your instance is running. If it ever reboots, you lose that parameter. So the second command there is what you can use to persist it across reboots. And then lastly, of course, this is only new connections going forward. So if you're trying to do some experiments and want to see the effects of this, you want to make sure you bounce all of your network processes to make sure they're all taking advantage of the new setting that you just set up. Okay, so let's talk a little bit more about the retransmission timer. So the retransmission timer is another one of these kind of finicky values that you have to take some care in selecting. The retransmission timer is important because it's the sender's perspective of when it has received an acknowledgement. So if you put the retransmission timeout too low, let's say I stick it at 100 milliseconds, and I'm communicating over a TCP connection that has a round trip time of 95 milliseconds, then it's very likely that a response will be on its way and just experience a little bit of jitter, and my RTO timer will fire, and so I'll initiate a retransmission just before the acknowledgement packet actually arrives. And so we're wasting work, and we're not doing the network any favor because we're adding packets that are ultimately going to be useless, and will add a little bit of congestion to the network too. Of course, on the flip side, you don't want to send it too high. If you set the RTO timer to say a second, and you have two instances which are right next to each other, and maybe they have a sub 1 millisecond round trip time, and if one of those packets does happen to get dropped, those instances are just going to sit there for the other 999 milliseconds waiting just in case for this packet to show up one day. And so if you set it too high, you can have these really long stalls in your network connection, which is almost as bad, right? So it's a little bit of an art about how to set this. On Linux, On Linux, the default is 200 milliseconds, and it's set again on a per route basis. When you list your routes, it's not going to show you the 200 because it is the default, but we can certainly update it. So let's update it to a smaller value for our local subnet. So if you're running two instances in the same subnet in, say, a VPC, those two instances will always be in the same availability zone, which means I'd expect, very low round trip time, on the order of 1 or maybe 2 milliseconds round trip time between those instances. So let's update just that, just that one route there, which is the link local route, which applies to all the instances in my in kind of my broadcast domain. So again, here's our route list. We can see what we're starting out with. And then I'm going to do IP route change. I'm going to set my retransmission minimum to 10 milliseconds. So this should be a pretty comfortable buffer so that if I see a little bit of jitter, it does happen from time to time. I shouldn't have any spurious retransmissions. But at the same time, I will actually react fairly quickly because my expected round trip time is so low. And then again, if I list my routes after the fact, we can see the RTO min there has been applied. So one of the things that actually can kind of contribute to retransmissions is what's called queuing on the network path. And so when you send a packet between two endpoints, what happens is it traverses some set of routers before it finally reaches its destination. Now, when a packet reaches a router in the middle of your network path, what happens is it arrives on an incoming network interface and it sits in a queue. The router then has a data plane which takes the packet off the queue, makes a routing decision as quickly as it can, and then sticks it on an outbound queue on the outbound interface. So we have two queues here on this router. And what we've discovered is that these queues can be subject to kind of microbursts of activity. So if you have a bunch of packets that all show up at exactly the same time and get pulled off the wire very, very close together, the routing engine can only process them at a certain speed. And so if you're at the back of the queue, you can observe latency increases simply by sitting in that queue for just a little bit of time. It doesn't necessarily mean the link itself is saturated. It means that a lot of packets showed up at exactly the same time, just a really quick microburst. And this can contribute to kind of the end-to-end latency of your system. And of course, when that happens, you can trigger retransmission timeouts. And again, this does not become from congestion, but it's from this kind of queuing behavior. So there's been a really interesting body of work that kind of looks into this problem to try to figure out, is there anything we can do about it? And it turns out there is. It's called active queue management. And what active queue management does, it has this observation that, the problem here is actually that microburst. So if I'm in a situation where I have routers whose interfaces might have kind of lengthy queues, it behooves me to try to insert just a little tiny bit of delay in between a few of my packets to try to spread them out. Right? If you think about what happens a lot of times from an end-to-end perspective of what's going on in the network, you oftentimes have big buffers which are copied in bulk, processed, and then another big bulk is applied. So the idea behind some of these algorithms is you want to try to take smaller chunks and put a little bit of spacing. So the end-to-end kind of bandwidth will be approximately the same, but the actual spacing between the packets is just enough to try to kind of elide this queuing problem. So the implementation I'm going to use here is called the CODL algorithm. CODL actually stands for controlled delay, because that's effectively what it's doing. It's putting in some very controlled, very selective bits of delay into the network. And this particular algorithm it comes standard on a lot of installations of Linux. It certainly is on Amazon Linux and many others, really. And so the way we're going to turn this on is using what's called the traffic control mechanism of Linux, so the TC command. So the TC command is one of these tools which is extremely powerful and is really rivaled by its learning curve. I mean, like it's a very hard tool to kind of figure out if you're just getting started. But the good news is that there's a lot of good documentation and particularly good examples out there for doing particular things with the TC command, even if you don't fully grok every little bit of its power. So here what I'm doing is I'm actually looking at what's called a queuing discipline. So I'm going to list my queuing disciplines. And the important line is that second one with the pound sign, which is I'm going to add a new entry in my queuing discipline, which says add this CODL algorithm. And so what this is going to do is that every time a packet leaves my Linux instance, it will be subject to this queuing discipline, and it will go through this CODL implementation. And so CODL is actually kind of neat. There's some more information here at that webpage. And what CODL actually tries to do is it tries to not make you make any decisions. It doesn't really have very many tuning parameters. And one of its strengths is that it just tries to be smart and tries to use a lot of heuristics to figure out things for you. And so we're going to look at this some more, again, once we get to our applications at the end. Okay. One other thing to keep in mind with TCP performance is, of course, the size of your packets. A lot of systems along the network path are ultimately limited by their packet per second performance, not necessarily their byte per second performance. So if you're thinking about making a routing decision on a packet, the routing decision just looks at the headers and then moves the entire packet all at once. And so what that means is that if we want to increase our throughput of the system for a given packet per second, it behooves us to increase our payload so that we can get a higher ratio of kind of bytes that were ultimately from the application into each packet. So if we start out with kind of a 1,500 byte packet, which is what you would have kind of standard on the internet, you get about 3.5% of overhead just from the IP and TCP, all the 2, 3, 4 layer headers that are on this packet that contribute to just waste, right? So what a lot of more recent networks use is 9,001 byte packets. This is what we use in VPC. So you'll actually get explicit signaling within your VPC that you can go up to 9,001 bytes. And we're going to look at some actual implications of these packet sizes in just a minute. But let's say we want to actually tweak it and play around for a little bit. So if we look at our local link using this IP link command, what we can see is that it's actually set to 9001, which is what we want. And if we show our route list, it doesn't really tell us much because it's kind of defaulting to its defaults, and it'll actually use path MTU discovery to figure out what MTU size to use. But let's say we want to change it anyway. We want to set it to something that we want to override. We can do that again on the route. So let's say we want to update our default route to our default gateway to explicitly always use an MTU of 1500. So we can do that with that IP route change command. And then once we list that, we can see the overridden output in the route list. Okay, a couple more things before we can dive into some of the applications. When it comes to packet per second performance, one of the really important things when working in a virtualization environment is to eliminate overhead in processing each packet. And so a couple years ago, we launched a feature called enhanced networking, which is available on a lot of the new VPC instance types. And what enhanced networking does is it allows the user, the guest operating systems, like your EC2 instance, to bypass the host operating system, like the hypervisor and the system that runs the different guest operating systems. It allows them to bypass those host operating systems and send packets directly to the NIC. So it basically exposes the hardware NIC directly to your VM image. And the advantage of this is that you get a lot less code touching the packet, which means there's a lot less latency, and almost more importantly, there's a lot less jitter. And so what this translates into in a virtualization environment is higher packet per second performance. And so anytime you're going to be running experiments within VPC, definitely make sure that you're using enhanced networking. It's been around for a couple years now, so it's the default almost everywhere. Certainly it's on the Windows AMIs and the Amazon Linux AMIs, but a lot of the other AMIs out there have switched to using it by default. If you want to learn some more about it, there's really good documentation on the internet, and there was a talk a couple years ago that dove into how it works and how you can make sure that your instance is actually taking advantage of it, because it does actually require a particular driver to activate. Okay, let's talk about how we can use these new tools that I've been going over today. I'm going to stand up a couple instances. These are pretty beefy instances, M4 10XLs. And I'm going to run Amazon Linux on them, and I'm going to perform a series of application kind of experiments to try to analyze what some of these tuning parameters can actually do for us. So all of these applications are going to be HTTP based, and all but one of them are actually going to use SSL. SSL is the new standard. Almost all connections these days should be using SSL. So it really makes sense, I think, whenever you're doing benchmarking for web traffic, is you should always be including SSL in the equation. I try to take a little bit of care in eliminating other variables in these experiments. Again, the goal was not exactly to produce an exact replica of a particular production environment. They're a little bit contrived, and so your mileage will probably vary depending on what different outcomes you would get with tuning some of these parameters. And so the point here is, again, here's a way we can test things, and if you can reproduce your own environment in an environment like VPC, you can do these tests as well with your particular applications and see what effect these tools have on those. So I'm not storing the data anywhere. The client just throws it away as soon as it receives it. I'm using a RAM file system, so the web server doesn't ever actually have to hit any kind of storage device, and all the bits are randomized. So there's no potential compression going on at any stage. Okay, so the Apache Bench tool is going to be my client. It gives you a whole bunch of statistics whenever you run it, and so this is an example output. Which is what's going to be fueling some of the numbers I'm going to be sharing on the next few slides. It's a really fun tool, and actually, if you're doing any kind of web-based benchmarking, it's a really great place to start because it's fairly straightforward to use. Okay, so let's talk about an application that might be experiencing loss. So in the beginning of the talk, I talked about just how bad loss is for a TCP connection, right? Because the TCP congestion control algorithm really tries to back off very aggressively because it thinks it can't send more traffic. And the way it backs off has a very large impact in how it actually is able to achieve different levels of performance. So I'd like to try to simulate an experience where I have an application and I artificially inject some loss into the network. So I'm going to use, again, Jack and Jill here, 2 test instances. These instances are going to be about 80 milliseconds apart in round trip time. And then I'm going to have 160 parallel streams just pounding them. And so the goal here is, in the presence of loss, how good can I do? Excuse me. So it's oftentimes hard to find a link with a very controlled amount of loss to run an experiment. And certainly we take operational excellence very, very seriously in Amazon and try to make sure that there's no loss anywhere on our network. But it does happen, especially if you go out to the internet and have mobile clients. So we need a way to simulate it in our test environment. So I'm going to simulate it again using this TC tool. So TC is very flexible in what it allows us to do with each packet leaving our box. And here is a command that will add an artificial amount of 0.2% loss to all of my outgoing packets from that instance. So again, how good can we do with 0.2% loss? So starting out, running my Apache benchmark, I'm getting a little over 4 gigabits per second. That's pretty good over 80 millisecond round trip time. Now let's introduce that loss. Bam. There went over half of my throughput. Just 0.2%. And my application is already really suffering. So what can we do? Well, we talked about a bunch of different techniques, so let's just try them. You know, a lot of these tools and a lot of these tuning parameters takes time to build intuitions about. And if you don't fully know where to start, you can just try them. So let's try tuning that initial congestion window. Well, turns out that was a bad idea. So maybe we won't do that. Let's try doubling the TCP buffers on the sender side. That also doesn't help. And so, you know, the reason I kind of put the sender side here is, you know, if you have a client-server architecture, you can't always affect what the client is doing. So it would be nice if we could try to tune the server to behave a slightly different way without having to force a kind of an application or a system change on our clients. But it turns out there's not really much that we can do here on updating the receive window on the sender side, and in fact, that actually makes things worse. So in reading about some of these congestion control algorithms, I noticed that the Illinois algorithm, there's a little bit of foreshadowing here, the Illinois algorithm actually was particularly built to handle loss a little bit better. So let's try plugging in the Illinois congestion control algorithm. Look at that. So it's magic, right? I'm pulling this magic rabbit out of my hat. And I get 137% increase in performance just by tuning the TCP connection control algorithm. So a lot of congestion control algorithms aren't really expecting loss. But if you're in a situation where you have persistent loss on the network and it comes and goes, then it might be something that you want to test and try to evaluate whether or not some of these different congestion control algorithms might be helpful to you. Let's talk about long, big transfers. So there's this nomenclature called big fat or long fat pipes, and it's oftentimes a ripe area for optimization because it comes back to that bandwidth delay product problem. So let's say we have 2 instances that are spread across an 80 millisecond path, and I want to transfer some pretty big files. I'm going to transfer 1 gigabyte files, and I'm going to get 8 parallel clients. And the goal is how much bandwidth, how good can I do across these fairly long links to try to get those 8 gig files transferred as quickly as possible. So if I run it just kind of flat out, I see about 2 gigabits per second. That's okay, not too bad. Let's try doubling the buffers on the server side. Man, still not a good idea. But of course, you know, on a big transfer like this, the impact you would expect is, of course, on the receiver, right? So the receiving side is the thing that has this buffer that's constantly getting filled as it's transferring all this data. So let's try doubling the receive window on the client side. Oh, yeah, that's better. So now we're getting about 2.4 gigabits per second, which is a nice little bump. So using these little tuning tools that we've talked about today, you know, we can start to try to tease apart where we can get some increases in our system. Let's try this active queue management. So each of these lines is going to be independent. I didn't mention that yet. Each of these lines is not, you know, I'm not doing the server side and the client side and the active queue management. So each of these are kind of in isolation. So if I just turn on active queue management in isolation, I also get a little bit of a bump, right? So, you know, understanding what kind of the queuing in the middle of the network has enabled me to get a few more percentile points of benefit from this test setup. All right, so I have 2 things that independently made things better. What's next? turn them both on, right? Let's turn them both on, and we've done even better. What about Illinois? Let's turn that on too. A little bit better still. So adding our magic hat back into the equation, we've now been able to, oops, I jumped the gun a little bit. That's right. So at this point, let's also turn on the server side because we've removed a lot of the restrictions from the client side. So let's try turning up those server side buffers as well. And we get just a little bit more performance out of that as well. And so one of the interesting things about that is, it was an experiment we did early and had overall negative effects. But as you start tuning, all of these parameters interact, right? And so it can be helpful to try out different combinations of parameters, although certainly starting with one at a time is definitely a good idea. So in the end, on this experiment, we got about 32% of increase in network performance, just by tuning and playing. And not all the choices were good ones, at least not initially. But as we continue to play, we can see that there's opportunities for improving these things. Okay, let's talk about a low RTT path. So this experiment is a little bit contrived, but I wanted to include it to kind of highlight what the effect of that MTU size was. So remember, we talked before about kind of the difference between 1,500 byte MTUs and 9,001 byte MTUs. So for this example application, I'm going to be moving really big files, like 10 gig files, and think of it kind of as like a backup in your local AZ kind of situation. And what would happen if I was actually not using the 9,001 byte MTU? So let's do this transfer, but force it to be a 1,500 byte MTU. So with a 1,500 MTU, I'm getting about a little under 9 gigabits per second. That's actually pretty good, right? That'll move quite a bit of data across the wire. Now let's turn on the 9,001 byte MTUs, and there we go. We get a nice improvement, somewhat expectedly, right? We're sending more bytes for the same number of packets. Now, when we were talking before about the active queue management, right, the active queue management was really intended for long network paths that have a lot of routers in the middle, and some of those routers might have these network interfaces and have kind of full queues. And one of the comments I made was that the active queue management algorithms try to be fairly smart and use heuristics about when to insert latency in between those packets. Because you might think, well, this controlled delay algorithm is a terrible idea for high throughput applications because you're adding latency. And so if you have a really small round trip time, that's the opposite of what you want. And it would be very susceptible to changes in those inter-packet delays. But it turns out that Coddle is actually pretty smart. And when you turn it on, it's smart enough not to do anything. So it's a fairly safe tool to kind of experiment with. And you can see that when you're getting really, really good throughput, it's not going to be adding that delay, and it's not going to be impacting your performance there especially on this example where you're on a local link with really, really good throughput. Okay, so MTUs gets you a little bit, so something to make sure if you're ever on a system and you're trying to tweak it a little bit, just something to double check. Okay, last application. In the beginning of the talk, I was talking about initial congestion windows, right? And the example I gave was a lot of web pages have small artifacts which tend to fit in that ones to tens of K of data and tend to be transferred over relatively short-lived connections. So let's build a test setup that tries to kind of tease this apart. So this is the one test I'm actually going to use HTTP just to kind of remove a variable and really focus in on this problem because it's going to be coming down to exactly how many packets I'm going to be transferring. But I'm going to have a huge number of concurrent connections. So 6,400 concurrent clients all trying to grab a 10K file all at once. And we're back to kind of our normal 80 millisecond link between these instances. So our goal here is actually going to be to minimize the latency of these connections. Not necessarily the bandwidth, but the latency, although obviously those are very, very related. So if I run this by default, I get about 2.5 gigabits per second. And it takes a little over 3 minutes to run. Not bad. Let's change our initial congestion window from 3 packets to 16 packets. Remember, this is going from 4,300 bytes before waiting for our initial acknowledgement to 23K before we get our initial acknowledgement. And we can see that we actually pull down the mean time to run this experiment by like almost 6 seconds, right? And that's because there's less time that the sender is sitting there waiting for that first acknowledgement. It can actually put more data on the wire up front, and it turns into an actual increase in performance. So tuning this initial congestion window can really help in these kinds of situations. Of course, if you're transferring a really long file over a very long-lived connection, that initial congestion window probably is not going to have a material difference on the end-to-end run, end-to-end execution time of that transfer. But if the transfer is short, then you will see it. Okay. Let's go ahead and turn on Illinois. So you might think that this is a talk about advertising the Illinois congestion control algorithm. It's not the intent. It was just something I've been playing around with. And what you can see is something actually very interesting here. When I turned on Illinois, my bandwidth went down, but so did my time. And so what actually is happening here is because it's a different algorithm, it's making slightly different choices. And so when I see this result, I think what's happening is that the number of outliers that are kind of shifting around the average have come down. And so Illinois is a little bit slower, but it's a little bit more consistent, right? So again, it's merely an anecdote of, can we play around with these different tuning parameters and see what effect they have on our system. So our magic hat there didn't do a whole lot, but it did bring down the mean time just a little bit. So 4.6%. Okay, so what should you take away from this talk? The one is that the network doesn't have to be a black box, right? There's tools out there that we can inspect what's going on your TCP connection, what are the retransmission settings, what are the timeout settings, what are the congestion window settings. We can start playing with these, and once you know where to look, then you can start having the fun time of experimentation, right? So spin up a few instances, run them for an hour, and just throw all these different techniques and see what you come up with. And after you do that a few times, you'll start to build some intuitions about what kinds of improvements you might expect in other environments. But they can be surprising from time to time as well. The other thing to take away from this talk is I never actually touched the application, right? I never made a change to Nginx. I never made a change to Apache Benchmark. These are all kind of Linux-level tuning parameters that you can apply even if you don't control the software that you have. So if you have third-party software or closed-source software, you don't necessarily are in a bind in that you can't change it. You have other options to change kind of the system-level parameters to try to get better performance, kind of independent of what the application is doing. And then finally, hopefully this will provide some insight into, what your application is actually needing, right? You want to make sure that if your application has a specific demand of the network, if you're using long paths with high RTTs or short RTTs, you can try to figure out what avenues to kind of tackle first. That's it. Thank you very much for coming to the talk. I really appreciate your time. Please remember to complete your evaluations. I'm happy to stay up here at the front if anybody has questions afterwards.